In this video, we're going to take a look at section 4.1 on exponential functions. An exponential function is a function of the form f of x equals a to the x minus h power plus k, where a is greater than 0 and a does not equal 1. So a here is the base of our exponent, and it will be a number. So this is going to be a little different than the exponents that we've been used to dealing with, because normally exponents have the variable as the base and then a number as the exponent. So you'd have something like x to the third power. We're going to flip that around in this section and look at things like 3 to the x power. So the number will be the base and the variable x will be in the exponent. Now, in order for that to work appropriately, that number cannot be negative, because if you have a negative base raised to a variable power, it will not behave very well. It'll be a very difficult mathematical function to study. And if a is equal to 1, well, then that's very boring, because 1 to any power is always going to equal 1. So 1 to the second power would be 1, 1 to the third power would be 1. So 1 to the x power would always just equal 1, and that wouldn't be a very interesting thing to study, so we exclude that as well. All right, so this is what an exponential function is. The minus h and the plus k are callbacks to chapter 2, where h is a horizontal translation. It will shift the graph to the left or to the right. And k is a vertical translation. It will shift the graph up or down. So keep that in mind when we get to the graphing part. All right. So here are some examples of what an exponential function might look like. So we have g of x equals 3 to the 1 minus x power. Here we're being asked to find g of 4. So just like we've done throughout the entire course, whenever they have a number here inside of the function, that means we want to plug that number in for x. So here we're going to be plugging in the number 4. So we'll have g of 4 equals 3 to the 1 minus 4 power, right? We're going to plug in the number 4 for x. This will give us 3 to the negative third power. And I chose this problem on purpose so that we would have a chance to talk about how to handle this when you have a negative exponent. So a negative exponent is processed by flipping it over to make it a positive exponent. So if we think of this as 3 to the negative third power over 1, we really can't evaluate what this is equal to while the exponent's negative. So what we do to make it positive is we flip it down to the bottom. And so since nothing will be left on top, we'll put a 1 in its place. And then we'll have 3 to the positive third power on the bottom. So when you flip it down to the bottom, the exponent becomes positive, and then we can evaluate it. 3 to the third power means 3 multiplied to itself 3 times. That's 3 times 3 times 3, which is going to be 27. So we get 1 over 27. All right, so when you have a negative exponent, it flips it over, and oftentimes when it's a whole number, which is what you should be dealing with most of the time, it'll flip it over and make it into a fraction. Negative exponent is in the denominator. It gets flipped up to the top, and maybe will not be a fraction anymore. So it just kind of depends on the situation. All right, let's take a look at this one. We have h of x equals 1/2 to the 1 minus x power. So again, what I'm trying to do with these examples is illustrate, the base can be just like a regular whole number, like 3, 4, 5, whatever, as big as you want. Or it could be a fraction, right? It could be between 0 and 1 as well. So it cannot equal 1, it can't be negative, but 1/2 is okay. And so we're being asked to find h of negative 1. So we'll take negative 1 and plug that in for x. So we'll have h of negative 1 equals 1/2 to the power of 1 minus negative 1. So this one, the tricky part is dealing with the double negatives. So a double negative here becomes positive. So we'll have 1/2 to the 1 plus 1 power, which is 2. And then another thing I wanted to illustrate with these examples is how to deal with a fraction that's being raised to a power. And it's a pretty easy thing to deal with, actually. You just take the exponent and apply it to the top and bottom of the fraction. So we're going to get 1 to the second power over 2 to the second power, which is going to give me 1 over 4. All right, Very good. Let's take a look at the next slide. So the next topic in section 4.1 evidently is graphing. And this is kind of my least favorite topic of chapter 4, because for the most part, these problems are fairly short. As you just saw the two examples we just did, you get through them pretty quickly. Even as we get to more complicated examples, the problems still tend to be fairly quick. Not that they're easy necessarily, but once you know how to do them, you can get through them pretty quickly. The graphing, however, is an exception to that. So here's an example from the textbook of what an exponential graph looks like. So here, the grayed out one, the one that's not colorful, is the graph of y equals 2 to the x power. Here, the base is bigger than 1, right? So here, the base, which we often refer to as the letter A, the base is bigger than 1. And so you get this increasing curve. So if you start from the left-hand side, and this is your eyeball here, and you look to the right, the graph is going up the whole way. So for an exponential function, when the base is bigger than 1, you will get an increasing curve. The red graph here, the one that's actually colorful, is the graph of f of x equals 1/2 to the x power. So for this particular graph, the base is smaller than 1. And whenever the base is smaller than 1, it has the same basic shape, but it's flipped around the other way so that it's a decreasing curve. And so this is, as you start from the left-hand side, again, this is your eyeball right here, and you go to the right, the graph is going down, and it just does that the whole way. You'll notice that whichever graph we're looking at, the gray one or the red one, it approaches the x-axis without crossing or touching. And so we saw this concept back in chapter 3. This is called an asymptote. And so I'll do my best to draw a straight line here, but the x-axis here, oh, that wasn't supposed to draw that in, is the asymptote for this graph. So this is an asymptote. And it's at y equals 0 initially. Now, you can memorize this if you'd like, that the asymptote is at y equals 0, but if the graph is moved from its basic position, the asymptote will also move. So if we shift this graph down 1, the asymptote will get shifted down 1 as well, and then it'll be at y equals -1. So just be aware that the asymptote won't stay here if the graph is being transformed in some way. All right, and so they give you some, like for the red graph anyways, they give you some points to consider, but again, those will also move as we do transformations. All right, so let's take a look at some graphing examples that you'll see on the homework. Okay, so use transformations to help graph the function f of x equals 2 to the x power minus 3, identify the domain and range, and the horizontal asymptote. Determine whether the function is increasing or decreasing. All right, so a lot of those things we just talked about on the previous slide. So this part of the homework throws students through a loop because it's a little different than what you've been asked to do before. But here, so the base is 2, right? So the points that they're gonna, now this is for my example, when you do the homework, you might have a different base. Your base might be 3 or it might be 5 or something like that. Whatever the base is for the function they're giving you, these points are points on the graph of the basic function with the same base. So the basic exponential function that has a base of 2 is just 2 to the x power, right? So this would be my parent function. This is the most basic exponential function with the same base. So it's going to be y equals 2 to the x power. Sorry about that. All right. And these points are on this particular graph. What they're asking us to do is to find out where will these points end up after the transformation is applied. So when we get to the graph that we're actually trying to find, where do these points end up moving to in getting there, right? So the point 1, 2 is a point on this basic function. However, it's going to move to a different spot for the new function that we were given. And so you'll have to be able to recognize, looking at the equation, what change or changes are occurring, and then apply those changes to these points. So if you remember from chapter 2, when you have a minus 3 tacked on to the end of your function, that is going to shift the graph down 3. Right? So the -3 on the end is going to be vertical. It's either going to be up or down. Because it's negative, it shifts it down by that many, by 3. So if we take this point, let's go ahead and mark it over here actually. So this is not a point that's going to be on our final graph. This is a point on the initial basic equations graph. We want to shift this point down 3. So if we start here at 1, 2, shifting it down 3 is going to bring it down to, I'm sorry, I didn't do a very good job of that. Let me try it again. It's going to bring it down to this point right here. Right? So we're at 2. 1, 2, 3 down will take me down to -1. So I'll get this point here that's at 1, -1. So that's where that point's going to end up. So it starts at 1, 2. After I shift it down 3, it ends up at 1, -1. So a shortcut for getting that result, instead of having to visualize it and to graph it, shifting down 3 is only going to affect the y-coordinate. The x-coordinate was not affected. So notice that the x-coordinate here is 1, the x-coordinate here is 1, it stayed the same. The x-coordinate didn't change. So for vertical shifting, the x-coordinate isn't affected. Only the y-coordinate was affected. It was at 2, it drops down to -1. And the way you get there is by subtracting 3. So we'll take the y-coordinate here for the basic point, subtract 3 from it to get the location of the new point, right, which will be at 1, -1. We'll do the same thing for the other 2 points that were given here. So for 0, 1, that point's going to get shifted down 3. So that means we'll subtract 3 off of the y-coordinate. The x-coordinate will stay the same. And so I'm going to get 0, -2. And saving the best for last, we have -1, 1/2. We want to subtract 3 off of the, well, let me try that negative sign again, off of the y-coordinate. So the x-coordinate will still be at -1, but the y-coordinate is going to change, and it's a fraction, so we have to be a little bit careful about that. So either, sorry, I'm trying not to let my hat hit the setup here, because then I know it makes a noise. I was testing it out earlier. I was like, I gotta be careful about that, and then I'm not being careful. So you want to subtract 3. So use a calculator or get a common denominator, right? So the common denominator would be 2, and so this is going to be 1/2 minus 6/2, which will be -5/2, right? So that'll be the new y-coordinate for the new graph. Right? And so all 3 of these points have to get typed into that one little box, right? Now, obviously, that little box isn't enough space for all 3 of these points, but it will expand as you type more things into it. The other tricky thing is you have to separate your points with commas. So you'll type in, and I don't think the order matters. So whatever order you type these in should be fine, but you want to make sure you put commas between each pair of points. Sorry, I'm getting too close. The writing pad's being kind of sensitive here. Okay, there you go. Put commas after your points. Right. So it's easy to make a typo there. So just be careful as you're typing it in. So I'll go ahead and plot the points that I have for my new graph. So I'm not really interested in graphing the basic function. We're not being asked to do that. We just want to graph the new function. So I'm just going to plot these new points. We already have 1, -1. We also need 0, -2. And then we also want -1, -5/2, which as a decimal is -2.5. Again, you can find that out by using a calculator or dividing it. Right. So it's going to look like this. And I've drawn this kind of badly enough that these kind of look like they're going to be on a straight line, but they're not. And if the base was a bigger number, it'd be more obvious that they're not all going to line up together. The other thing that will help us with drawing our graph is knowing where the asymptote is located. I keep hitting the setup. I'm sorry about that. The asymptote also gets shifted down 3. So maybe we do need to go ahead and draw our basic function. So our basic function looks like this. Right, it's just this is a really rough sketch of what it looks like. And then the asymptote is located initially on the x-axis. When we shift this graph down by 3, the asymptote will also get shifted down 3. So it's starting on the y-axis, which is where x is equal to 0. If I shift that down 3, the asymptote will end up at y equals negative 3. Sorry, I'm saying I made the same mistake over here, so I apologize for that. Where's my eraser at? Okay, so it's not x equals 0, it's y equals 0. I apologize that I made that mistake. So this line here is at y equals 0, which is the x-axis. It gets shifted down 3, so now it's at y equals negative 3. And so it asks for the asymptote. That's what you're going to have to type in. Y equals negative 3 is the location of the asymptote. Let me see if I can draw it again. I'm doing a pretty horrible job here. Okay, oh gosh. So, okay, that didn't work out real great. Sorry. So there, it's located right there. On Math Excel, you won't have to actually draw it in yourself. Math Excel has a graphing tool for you to use, which is also a little different than what you've experienced previously in the course. I may need to make a tutorial video, a separate video showing you how to use the graphing tool, because a lot of students end up having trouble figuring it out. But once I show you, you'll realize, oh, it's not as bad as it seems, but there's just different options and whatnot. So I will make a video for that maybe tomorrow and send that out to you guys. All right, so now if you're drawing it by hand, you do need to draw this in, the asymptote. You need to plot these points, and then you want to connect the points according to this pattern to make it look like this shape here, the exponential curve, right? So going to the left, it will approach the asymptote without crossing or touching, so something like that. And then going to the right, you're going to get this really sharp curve upward. This is called a J-bend, is often the way it's described. And that's what's going to happen here. It's going to go quite vertical from there. With a base of 2, it's a little more gradual. The bigger the base is, the more sharp this curve becomes. So if the base is 10, it's a very quick curve upward. But it's going to look something like this. Now, from this picture, you should be able to figure out the domain and the range, right? So that's a couple other things they were asking about here. So the domain, remember, we've done this almost in every chapter. How far to the left? How far to the right? It goes forever to the left, so that's negative infinity. And while it's curving very sharply upward, it does go forever to the right. It's going to keep going to the right as it goes up. It just mostly goes up as it inches to the right, but it does that forever. So it'll go to it'll go to positive infinity to the right. For the range, how far down does it go? Well, it actually does have a limit. It won't go past negative 3. And here's where things are a little different than what we've experienced before as well. It's parentheses negative 3, not bracket, because it never actually reaches negative 3. It'll get closer and closer and closer to negative 3, but it never touches, never crosses. So we do not include the negative 3. It'll get all the way down to negative 2.9999999 eventually, but it will never ever reach negative 3. How far up? That one's pretty obvious. It goes to infinity. Right. And is this increasing or decreasing? It is increasing. If the base is bigger than 1, it will stay increasing. Unless the exponent's negative. That's a weird case that we might actually see on the next example. But we can see in our graph it's increasing. Now, unfortunately, it really should just give you the option of saying increasing or decreasing, yes or no. But it makes you type a little bit more in. So you have to first of all select increasing, and then it wants to know where is it increasing. Well, it's increasing everywhere. From the left-hand side, negative infinity, all the way to the right-hand side, positive infinity. So this is what you'll have to type in the Math Excel. It's increasing negative infinity to positive infinity. All right, let's take a look at, I think I have one more graphing example here, so let's take a look at that. So like I said, I had a feeling that I had a negative sign in here. And this problem I maybe need to remove from the homework. Excuse me, I need to take a drink real quick. Because this negative sign here represents a transformation that we actually did not study in chapter 2. And on paper, it's not too hard to deal with, but on the graphing tool with Math Excel, you kind of have to know that transformation, which we never actually did. So what's going on here? Let me rewrite this equation down here. We have y equals negative 7 to the negative x power. we did talk about this negative sign in chapter 2. This flips the graph over. And in chapter 2, that was a sufficient description because it was the only kind of flipping that we were doing. And so if we just said flip, it meant flip over the x-axis. And like I said, because we weren't studying any other kind of flips, just saying it flipped was enough. But here we actually need to be a little more precise about it. So this negative sign flips the graph over the x-axis. Right. So it's gonna flip it over this way. This negative sign up here, let me pick a different color, is also a flip, but it's a flip that we did not study in chapter 2. But you could probably guess, if this is flipping over the x-axis, this is going to flip it over the y-axis. Right. And so the graph gets flipped twice. Now the way you can manage that without knowing this second transformation, flipping over the y-axis, is using what we talked about earlier in this video. The negative exponent can be made positive, so I'm going to rewrite this equation down here, by flipping the base over, right? So the negative sign stays where it is. The base, however, gets flipped over and becomes 1/7, and that makes the exponent positive. And that way you don't have to deal with flipping over the y-axis. This takes care of it for you. However, if you do this on Math Excel, I don't know if it will accept this as the right answer because it's expecting you to work off of this one, not off of this one. So I guess you kind of need to know this way, which is, like I said, maybe a reason for me to remove this problem from the homework. Now we have to track where all these points will end up going when these transformations get applied. So 1,7, let's go ahead and visualize that point. This is on the original basic function, right? So the basic one that we're working from is y equals 7 to the x power. So like I said, this is the basic exponential function of the same base. The base here is 7, so we want to use the same base for our basic function. But the shape of the graph is just the same as what we did in the last example. It's going to look like this, right? And we'll have an asymptote here on the x-axis. And so we get this point here. We also have the point 0, 1, which is right here. And we have the point -1, -1/7. And so here you can see the curve is much more dramatic than it was when the base was 2. So I want to flip this graph over. I'm not going to draw it in, but you can imagine what the graph looks like here. We want to flip it over the x-axis and then flip it over the y-axis. So let's start with this point here. This point that's at 1,7. If we flip it over the x-axis, this point gets flipped over the x-axis and it will be at 1, -7. But then we also want to flip it over the y-axis. So if I flip this point here over the y-axis as well, it ends up here at -1, -7. So this point that starts at 1, after you do the transformations, it will end up at -1, -7. And so that point needs to get typed into that box. Maybe you can see the shortcut here that instead of having to visualize it, we just take this point, change the sign of the x coordinate, and then also change the sign of the y coordinate. And that applies to 2 transformations. So if we do the same thing with this point, change the sign of 0, well, it's still going to be 0 because 0 doesn't have a sign. Change the sign of 1, it becomes -1. And so that's where this point will end up. This one, same thing, change the sign of the x coordinate so it becomes +1. Change the sign of the y coordinate so it becomes -1/7. And so those are the 3 points that you want to type into this box. So let's go ahead and plot these other 2 points. We have 0, -1, and we have 1, -7. 1, -1/7, which is going to be really, really close to 0. Right. Now the asymptote, so if you take this graph here, flip it over the x-axis, flip it over the y-axis, the asymptote doesn't go anywhere, right? Flipping it over the x-axis doesn't move the asymptote. Flipping it over the y-axis doesn't move the asymptote. So the asymptote actually doesn't change. It stays exactly where it started, which is the x-axis. And I can't draw a straight line on this thing, sorry. I feel kind of bad about that. Let me Let me try one more time. Let's see. Maybe if I take my time with it. There we go. It's a little better. Okay. And then you can see the curve here. So the curve, the J-bend of the curve is right here. Going to the right, it's going to approach the asymptote without crossing. And going to the left, it's just going to go down very sharply, right? And so let's start from maybe right here. It's going to approach the asymptote without crossing, going that way. And then going to the left, oh, I kind of missed the mark there. Let's try it again. It's a very sharp curve. I'm sorry, next time I won't wear a hat when I'm making my lecture video. So I keep hitting the setup. All right, and so the graph looks something like this, maybe a little bit more connected. But that's how you would draw it by hand. Okay, the domain, you'll find this out pretty quickly, is always negative infinity to infinity. All right, for these exponential functions, that's always the domain. The range, how far down does it go? That's pretty obvious. It goes down to negative infinity. How far up is it going to go? It won't pass 0, and it never reaches 0. So we have to use parentheses on that, not a bracket. So there's our domain and range. The horizontal asymptote never moved. It stayed at y equals 0. Sorry about that. And is it increasing or decreasing? Well, when the base is less than 1, this becomes a base of 1/7 if you process it this way. That's decreasing. But then when you flip it over the x-axis, it becomes increasing again. So just again, look at the final product here. The graph, you can see as you go from left to right, the graph is just going up the whole way. So it's actually increasing, and it's doing that the whole way from negative infinity. Sorry about that. I don't know what I'm doing. I thought I disabled it. So the pen I'm using has like a little button on it that if you press it, it erases instead of writes. And so I keep accidentally pressing the button. And like I said, I thought I disabled it from doing that, but I guess I didn't. All right, so that answers everything. And this is why I don't like the graphing in section 4.1, because we just spent like 20 minutes on it. It's going to be maybe 4 or 5 problems on the homework. It's going to be 1 or 2 questions on the test. So it's really not the main focus of chapter 4, but it still takes up a disproportionate amount of time. So let's move on to another topic, a better topic. Solving exponential equations. So I'm putting here technique number 1. And if I recall, my lecture outlines, I kind of mess up on the numbering later. But the main thing I want to draw your attention to is that there's more than one way to solve an exponential equation. And the method we're going to learn today is the best method. It's the easiest method to use. And so we always want to try this method first to solve exponential equations. And in this section, this method will work on all the problems. In later sections, we'll have exponential equations where this method doesn't work, and we have to do something that's a little more difficult. So this method, what's nice about it is, it's a pretty straightforward technique, especially with the examples that we have here. You get both sides to have the same base. This is probably the hardest part of the problem. You have to rewrite both sides of your equation as exponents with the same base for this technique to work. If you can't write both sides with the same base, that's when this technique fails and you have to do a more complicated thing. But in section 4.1, you should always be able to do this with these problems. Then you set the exponents equal to each other. So the only way 2 expressions can be the same, or sorry, how do I want to say this? The only way 2 expressions can be equal to each other that have the same base is for the exponents to be equal to each other as well. And so once you get both sides that have the same base, you set the exponents equal to each other because that's the only way that equation can be true. And then you can just solve it for x. And usually you'll get a really easy equation to solve for x. So it won't be anything crazy like a quadratic equation or anything like that. All right, so let's apply this technique to some problems here. So we have solve the following equation. 4 to the negative x power equals 64. The first step is to rewrite both sides of the equation as exponents with the same base. So let me just rewrite the problem here instead of marking up on the original problem. So here's our problem again. The sorry, I'm saying the wrong side. The left-hand side, I keep hitting this thing too, I'm sorry. The left-hand side has a base of 4. Right? It's already an exponent, it already has a base of 4. So the first thing you should try to do is, can I rewrite the right-hand side with the same base. I want to rewrite it as an exponent, and I also want the base to be 4 because then they'll match each other. And it turns out with this one you can. So hopefully you're somewhat familiar with basic, powers, like 2 to the 5th power. That's 32. That's a good one to know. 2 to the 4th power, 16. 3 to the 3rd power, we saw that earlier. That's 27. You kind of want to know those basic ones. That'll help you a lot with these problems here. 64 is actually 4 to the 3rd power. If you didn't know that, that's fine. Use a calculator and experiment. Try it. 4 to the 2nd power, that's 16. 4 to the 4th power, that's 256. So try some different numbers and see if you can get one to work. And once you try 4 to the 3rd power, you'll realize that's the one you're looking for. So 4 to the 3rd power is 64. I'll leave the left-hand side the way it was already given to me. And that's step 1. Rewrite both sides of the equation as exponents with the same base. Step 2 is set the exponents equal to each other. So I can take the exponent from the left-hand side and the exponent from the right-hand side and set them equal to each other. All right, I hit that button again. All right, and so we get negative x equals 3. I want to be clear that while it might look like this is what I'm doing, I am not canceling out these bases of 4. So I think some students think, oh, you're just canceling out the 4s, which in a way is possible to do, but we haven't talked about how to do that yet. And I don't want you to get the wrong idea about how this works. So I really would advise not thinking of it like this. I'm going to undo those marks. I am not canceling out the bases. I'm just using this property that if the bases are the same, then the exponents have to be equal to each other when you have an equation like this. All right. And so I set the exponents equal to each other, and I'm ignoring the bases. I'm not canceling them out. I'm just bypassing them. All right. And then step 3, the easy part, is now you can solve this for x to solve the equation. So solve this for x. We divide negative 1 on both sides, and we get x is equal to negative 3. And there's our solution. So that's all there is to that. Let's take a look at another one. So here we have 2 to the x power equals 1 over 16. So again, step 1, write both sides so that they have the same base. The left-hand side is already an exponent with a base of 2. So ideally, I'd like to rewrite the right-hand side as an exponent with a base of 2. Sometimes you might not be able to do that. Sometimes the numbers might not quite work out where that's possible, but most of these problems you should be able to do that. Now, how do I get from 1 over 16 to an exponent with a base of 2? Well, again, if you know some of these basic powers, you would know that I just talked about this one on the last slide, actually. 16, we know, is 2 to the 4th power. Right? And if you didn't know that, again, use your calculator, try some numbers out. 2 to the 2nd power is 4. 2 to the 3rd power is 8. 2 to the 4th power, that's 16. But I don't want 16, I want 1 over 16. So how would I make it a fraction? What would I have to make the exponent in order to make it come out as a fraction? You'd have to make it negative, right? So we talked about that earlier in the lesson as well. So let me put it this way. If 2 to the 4th power, let's say it the other way around. 16 is 2 to the 4th power. So 1 over 16, and I locked up there for a second, sorry. If I paused without moving, oh gosh, okay, what's going on? No. Okay, sorry about that. My computer froze up on me, so I had to pause it, and hopefully I've cut out the part where I'm probably looking confused about what's going on. All right, so that's step 1. Get both sides to have the same base. Step 2, set the exponents equal to each other. So we take the exponent from the left-hand side, which is x, set it equal to the exponent from the right-hand side, which is negative 4. And then step 3, in this case, there's not even anything to do. It's already solved for x, so that's our solution. Let's take a look at another example. So this one's a little tricky. We can't quite do it the same way we've done the previous two. So what we've done in the previous two examples is we've said, oh, we already have an exponent on the left-hand side. So let's rewrite the right-hand side as an exponent with the same base. In this case, the base of my exponent is 32 on the left-hand side. So if I'm following the same logic, I would want to rewrite the right-hand side with the same base, 32. So I have to be able to take 2 and rewrite it as an exponent as 32 to some power. And it's possible, but it's awkward, and it's maybe going to be hard to figure out. So actually, in this case, we're going to go the other direction. I'm going to leave the right-hand side as a 2, and I can make that an exponent by thinking of it as being to the first power, right? This is 2 to the first power. That makes the base a 2. The exponent is a 1. And I want to rewrite the 32 as 2 to some power. And then I'll raise that to the x power, right? So I'm going to take the 32 and think of it as 2 to some power. And again, you might have to check on your calculator till you find one that works, but you should find eventually that 32 is 2 to the 5th power. And then I'm going to raise that to the x power and set that equal to 2 to the 1st power. So I'm replacing. So how do I want to write this here? I have 32 to the x power equals 2. I'm rewriting it like this. I'm rewriting the 32 as 2 to the 5th power, copying the x down as an exponent, and then the right-hand side, I'm rewriting 2 as 2 to the 1st power. Now what you need to know is whenever you have one base with 2 exponents acting on it, you multiply those exponents together. So I'm going to simplify this by multiplying 5 times x together, which gives me 5x. All right. But the parentheses won't be there anymore. That's the important thing, is you want to rewrite this so that it's not complicated like this. You just want one base with one exponent. So, and you need to know, in order to get that, you multiply these together. Now, this is step 1. Now that I have the same base, I set the exponents equal to each other. Right? And so I'll take the exponent from the left-hand side, which is 5x, set it equal to the exponent from the right-hand side, which is 1. That's step 2. And then step 3, we solve for x by dividing 5 on both sides. And so we get that this is step 3, we get x is equal to 1/5. All right, and that solves the equation. All right, now this problem looks different, but it actually is the same exact problem that we were just doing. It's just set up in a different way. So here we're given this function, f of x equals 2 to the x power. And they want us to find x if f of x is equal to 8. So if you think back to the beginning of this video, we started off looking at functions. But in those cases, we were plugging numbers in for x and we were finding y. This is flipping that around. They're giving us the y value and they want us to plug that in and find x. So don't take 8 and plug that in for x. That's not what they're asking you to do here. They're telling you to take 8 and plug that in for y. Right, so remember, f of x is my y variable, and I'm going to plug 8 in for that. Right, so I'm replacing the function notation with 8, and then I'm going to find x. What is x equal to in this case? Right, and so once you set that up, you see that this problem comes out exactly the same as the problems we were just doing. We have this equation that we want to solve, and in order to do that, we have to get both sides to have the same base. Now, normally I would have made this point earlier on my first example, but I forgot. And so I'm going to make the point now, which is what you cannot do with these equations is you can't solve this for x by dividing 2 on both sides. That's a common mistake that students will make. They think, okay, I'll cancel out the 2's by dividing a 2. And they think the 2's cancel out and they'll get x equals 4. But that is not what happens here. The 2's do not cancel out because this is an exponent. You have to think of the 2 as an exponent as well. And when you're dividing, the bases don't cancel out. What happens is you subtract the exponents. So the base will stay a 2, and then you take the top power minus the bottom power. You subtract the exponents, and you get x minus 1 is equal to 4. And so you see you're really in the same boat. Your x is still stuck in the exponent. You're not going to be able, no matter how many times you try to divide by 2, you'll never get x down on the ground where you can solve for it. So that just doesn't work. You can't solve these exponential equations by dividing on both sides. Dividing is not effective here. So what is effective, starting over again, is what we did on the previous few examples. rewrite both sides as exponents with the same base. I'm going to rewrite the 8 as 2 to the third power. Now that both sides have the same base, I can set the exponents equal to each other. So I'm going to take this exponent, which is 3, set it equal to this exponent, which is x. And then if necessary, you solve that for x. This is already solved for x, so we're done right away. All right. The last type of problem in this section, so I'm sorry, I keep hitting this thing, I'm sorry. In class when I'm teaching, we have a 50-minute block of time, and I usually struggle to get through an entire lesson in 50 minutes. With videos, I'm able to just keep moving from one example to the other, so usually I get through a little bit quicker. And hopefully most of my videos will be shorter than 50 minutes, but this one I can see is already at the 40-minute mark. So I do apologize for the length of this video. Hopefully they'll get shorter as we go. So I have one more type of problem to look at, which is these compound interest problems. So here we have a deposit of $6,000 that earns 3% annual interest. So it's an interest problem. So it might make you think of this formula that you might have used in the past, which is I equals PR, which, by the way, is a little bit of an abbreviation. There's really a time component here that the problems you dealt with in the past were able to ignore because they always set the time to 1 year. But if the time was more than 1 year, you'd have to multiply by the time here as well. And this is actually part of a bigger formula, this. So A equals P plus PRT. Right. And so this is the interest part of that calculation. And that interest gets added to the amount you have invested, and that tells you the total amount of money that you have altogether. This is for simple interest, which unfortunately is not very common in the real world. The math is easier. That's why we start with that concept, because it's easier to do mathematically. But that's not the way financing is set up in the real world. So in the real world, we use compound interest for almost everything. So whenever you take out a loan, whenever, like your student loans, most of them will have compound interest. Your credit cards have compounded interest. If you have an investment, like if you put money in a bank, like in a bond or something like that, that's also going to be compound interest. So whether you're borrowing money or investing money, the interest that's accrued, or like when you get a mortgage, like when you buy a house, it's compound interest. So this formula doesn't work for any of that stuff. It doesn't work for anything that you're going to actually encounter in the real world for the most part. It's compound interest that gets used. All right, and what happens with compound interest is every so often, either annually, quarterly, monthly, daily, those are very common periods of time, the institution that's in charge of the financial situation will stop and calculate the interest that you either owe or that you've earned on your investment. And then they add it to the amount that you owe or the amount of your investment. So let's maybe not think about owing money, because that's not fun to think about anyways. Let's think about you've invested money. So you have $6,000 invested. Well, if you compound the interest annually, that means once every year, the institution will stop and calculate your interest on your investment. And whatever interest you've earned, instead of cutting you a check for that money or putting it in a separate account, they reinvest it for you. They add it to your investment. So now your investment's more than it was before. It won't be $6,000 anymore. It'll be a bigger amount. And then the next year when they calculate it, it's calculated off of that bigger amount. And then you get even more interest, which gets reinvested for you. And then the next year after that, they will calculate it on that even bigger amount. So it not only does your investment grow, it grows by more and more each time because your investment's getting bigger and bigger. So essentially, compound interest is your interest is being reinvested for you periodically, either once a year, once a quarter, once a month, or every day. So the formula, it's a much more complicated thing, mathematically speaking. And so the formula is going to be more complicated, right? So we can't use this formula for compound interest. We have to use this other formula. It's A equals P times parentheses 1 plus R over N to the power of NT. Now, most of these variables you should recognize from over here. P is the principal, and that's the initial principal, how much you start with. R is your interest rate. It's your annual interest rate, which is usually what they're going to give you. T is the amount of time that you're going to let the investment run. So I guess let's go ahead and mark these in our problem. So this is R. This is P. This is the amount we're initially investing. T is the time, which is given here as 7 years. N is the only variable that you would not be familiar with from this formula. And N represents how often per year your interest is compounded. So if we're compounding annually, that's once per year. N is equal to 1. If we're compounding quarterly, that's 4 times per year. So N is equal to 4. If we're compounding monthly, that's 12 times per year. So N is equal to 12. And if we're compounding daily, that's 365 times a year, because that's how many days there are in a year. So those are the values for N based on these periods of time. So really, in the past, I was a little bit dismissive of this problem because it looks like a word problem, but I don't quite fit it in that category. There are a lot of words here, but really it's just a formula problem. It's plug and chug is what we would call this. So you take the numbers, dump them into the formula, dump that into your calculator, and it spits out an answer. And that's really all there is to this problem, but it is a complicated formula. And I've noticed that my students struggled with getting that formula into their calculator. I think they were okay on paper, but actually getting the answer out of their calculator was a little bit more difficult for them. And unfortunately, I don't have a calculator with me at home. I'm trying to think. I'm a math teacher without a calculator. But I'm trying to think. Maybe I could pause my recording, see if I could find something online, like an online calculator, so I can show you how to input it. So I'm sure there's some TI simulator out there or something I can use. But let's go ahead and do the paperwork part of it first. So I'm going to do 2 of these. I'm not going to do all 4 of them because they work the same. Almost everybody gets part A right. So because I used to have this problem on the test, everybody would get part A right, but then some people just messed up the rest of them. So it gets more challenging when N is a different number. So let's go ahead and plug, we'll do part A first, right? So we're going to find the amount after 7 years if the interest is compounded annually. So we'll have $6,000 that we start with. Plug that in for P. The interest rate is 3%. And just like any formula, pretty much any formula, you want to convert that to decimal. So it's 0.03. N is equal to 1 in this case because we're compounding it annually. And so that takes care of the parentheses part. And then the exponent here, N is 1 times T, which is 7. Right? So on paper, that's it. You just plug those numbers in to those variables, and this is going to be your answer. And so I'm going to pause here for a moment, see if I can find a calculator that I can maybe show you how to type that in, and then we'll get an answer for this here in just a second. Okay, so I tried to find something a little bit more realistic, but I ended up settling on my Windows calculator app. So I think this will get the point across. So we're going to type this into our calculator. 6,000, let's try that again. 6,000 times, so for me to do that, I'm going to have to hit the times key there. On the TI calculator, you shouldn't have to hit times. You could just put parentheses. 1 plus 0.03 divided by 1. Close the parentheses. So you can kind of see it populating in that gray area just above the 1.03. I want to raise that to the power. Now here's where students, I think, will often make a mistake. Now here with a 1, we know that's 1 times 7, which is just 7. We could just put a 7 there. But for more complicated numbers, you're going to have 2 numbers you want to put there. Like for monthly, it'll be 12 times 7. And so to get the calculator to compute that properly, even though we don't have to do this on paper, when you're writing it all in a single line on a calculator, you need to use parentheses for that exponent, since there's 2 numbers in that exponent. If you don't use parentheses, it just thinks the first number is there. It doesn't think the second number is part of that exponent. So I need to use parentheses here, 1 times 7. All right, so that's how it needs to look in your calculator for it to compute the correct answer. If you don't use parentheses on this, you will get the wrong answer. All right, so let's see what that's equal to. All right, so we have 7,000 $7,379.24. So let's see if I can remember that. 737924. All right. So 7379.24. I think I got that right. Now make sure you round this last digit properly. So this is the second decimal place where, it's the cents value place. And it happened to be a 4 for this particular calculation. Okay, I can't find my calculator again. Okay, there it is. So it happened to be a 4 here, but I kept it a 4 because this one was a 3, right? Because of that 3 there. If that had been a 5 or higher, I would have rounded this up to a 5. So you need to make sure you follow the proper rounding rules for that. All right, so this would be our answer for the amount. It also wants us to find the interest earned. So the way you calculate the interest is there's not a formula for it. This is the total amount that you now have in your investment. You subtract how much you started with, right? We started with $6,000. And so our interest is going to be $1,379.24. Right? So this would be the interest earned. All right. So this would be the amount. And then that would be the interest. So you type both of those numbers into Math Excel. That's for part A. Let's also try to see if I can squeeze part B in right here. I didn't leave myself a lot of room. So part B, or not part B, so we're going to skip that one. Well, let's do part C. Monthly is a very common time frame for a lot of financial calculations. So we'll have 1 plus 0.03. This time we're going to use 12 instead of 1 for N. Everything else will stay the same though, right? Still 7 years, still 3% interest, still $6,000 we're investing, but now we're going to compound it monthly. Now you might think, oh, this will be like 12 times as much money if we're going to compound it 12 times as often, but that's not quite how it works. So if they're going to compound it monthly, the annual rate is still 3%. So they take that 3% annual rate and they divide it equally for the 12 months. So essentially, that's why you're doing the 0.03 divided by 12. You're dividing up that interest rate and applying it a 12th of it to each month. And so it's going to be a much smaller rate that you're getting per month for your interest, but you are adding it to your investment each month. So your investment's going to grow a little bit more quickly. So you'll see we're going to have more money if we compound it monthly, but not like a ton more. It might be like $100 or something. So let's find out. All right, so let's go back to our calculator. Let's clear this out and let's type this calculation in. So we have 6,000 times parentheses 1 plus 0.03 divided by 12 this time, close parentheses, exponent, critical here, you have to use parentheses, 12 times 7 in the exponent. Right? Otherwise, you're not going to get the right answer. So that's what it should look like when you type the whole thing in your calculator at once. And so now we will hit enter and we get $1,400.13, right? Because I'm going to round the 12 here up because of that 8. So 7,400.13, right? And so that's what I'm going to get for the final amount here, 7,400. So I said $100. I was way off. I guess because the interest rate's kind of low. It was only like $20 more, right? So it does net you some more money, but it's diminishing returns. So if we compounded it daily, it might be $5 more than what we get for monthly, right? It's just going to go up just a little bit more. And that's over a 7-year period. All right. The interest is calculated in the same way. So the interest here would be $1,400.13. All right. So I'm sorry, this has gone on for quite a while. Looks like I have 2 more examples here. So I guess I'll do one of these, and I'm going to do the one with the hard amount of time. And then, because, 2 years is not going to be that bad, but 5 years, 7 months, 8 days, that's kind of an annoying thing to deal with. And then I guess I'll go ahead and do this last one as well, because I don't want to leave you hanging on that one. So I apologize. This video went on a little bit longer than I intended. A particular savings bank pays 8% annual interest compounded continuously. So this is different than our previous problem. Our previous problem was compounded annually, compounded monthly, compounded daily. This is compounded continuously, meaning they never stop calculating your interest and adding it back to your investment. It's just nonstop happening every millisecond, every split second. The formula changes because of this. So basically, n becomes infinity. You're going to compound it an infinite number of times per year. And that is kind of weird to be plugging in infinity for n. And you would think that the whole equation would be messed up from that. But actually, it sort of balances itself out. So in this formula, when n is infinite, you're dividing by an infinity, but then you're raising it to an infinity power. And those kind of balance each other out in a weird way. And the way it gets balanced out is it becomes this formula here. A equals P e to the RT. So if it says compounded continuously, you got to switch over to this formula here. Notice n is not part of this formula anymore because we're compounding it infinitely many times. And what is now part of this formula is e, which is not a variable. It's a letter, but it's like pi. Pi is a letter. It's a Greek letter, but it's a letter, and it represents the number 3.1415, ... E is functioning in the same way here. E is representing a number that has this run-on decimal that we don't want to have to write out. And that run-on decimal is something like 2.71, something after that. This is called Euler's number. Right. So if you want to look it up, it's a really fascinating number. It shows up in all sorts of unexpected places. It's a very common number in nature. All right. All the other variables mean what they meant before. R is the interest rate, T is the time in years, that's the important part here, and P is the principal. So again, it's another plug and chug type of situation. So let's do part C because the time there is going to be the most difficult one to deal with. So we're going to have A equals P, which in this problem is $7,000. That's our initial investment. E to the power of R, which is 8%, which we have to write as a decimal, so 0.08, times the time, which is going to be 5 years, 7 months, and 8 days. So what we have to do, we already have 5 years, but the time here has to be completely in years, right? So I can't have months, I can't have days. I have to convert those numbers into years. Now, my instinct tells me to take the 7 months and convert that to years by dividing it by 12, right? 24 months is 2 years. So you divide by 12 to get the number of years. So 7 over 12 would be how many years that is. But if you look at the hint here, that kind of indicates they don't want you to do it that way. So I would like to do it that way. That seems simpler to me, but they're saying up here 365 days per year and 30 days per month. So I think what they're asking us to do with that is to convert the months into days first, and then add it to the 8 days that we have here, and then convert the days into years. I know it seems a little bit convoluted, but that's the way I've been doing it. I haven't had any complaints from students, so I think that's the right way that MathXL wants us to do it. So 7 months, if there's 30 days per month, we multiply it by 30, and that gives me 210 days, right? As an estimate. Of course, it matters which months we're actually talking about. If you have February in there, that's 28 days. If you have April, that's 30 days. If you have, July, I think that has 31 days, right? So it could be a little bit off, but it's an average. 30 days just gives us an estimate. And then, so that's the months part, 210 days. We also want to add this 8 days to that, right? And so that gives me 218 days altogether. That needs to be converted into years by dividing by 365, right? So if you have a certain number of days and you want to know how many years that is, you divide by 365 to get the number of years. So we'll do the same thing here. Even though it's an awful, awful fraction, that's still how you convert it to years. So this is now in years. 218 over 365. That has to get added to the 5 years that we have out here. So it's going to be 5 years and then another 218 over 365 of a year with that, right? So if you want on your calculator, you can just plug that in and get a decimal. Just don't round that decimal off. You need this calculation to be as precise as possible. And so to keep it precise, keep as many decimal places as your calculator provides you, right? But that's how we convert it. I'm sorry things got a little bit cluttered here. Let me try that again. All right. And so this is what our formula looks like. If you want, it's a plus sign here, but you don't have to write the plus sign. But when you go to type it into your calculator, if you're going to leave it as a fraction, you got to think of that as a plus sign, and you probably need to put parentheses around this as well. So here's how I'm going to type it into my calculator. All right. So let's clear it out. We're going to have 7,000. Oh, does it have E on here? I don't know if it does. Let's try this. 7,000 times, I think this is going to be E. No, it just does exponent. Oh, it's right here. Okay, E. Yikes. Okay, so it gives us E as a decimal. So let's see if this is going to work. So that's E. I'm hopefully multiplying it to the 7,000. Raised to the power of, okay, it worked. It's a crazy long number, but it worked. Raised to the power of, we have to use parentheses again for our exponent. If we don't, it's a mistake. So we have to have 0.08 times parentheses again for the time. We have 5 years plus another 218 over 365. Close those parentheses for the time, and then close the parentheses again for the exponent. Right, so I'm closing these parentheses here. That's the time part. And then I'm closing these parentheses for the exponent. And so that should give me the correct answer when I hit enter. So let's see what we get. Hopefully it should be something more than 7,000, right? It should be like $8,000, $9,000, something like that. Oh, 10,000. Wow, it's pretty big. Okay. So, and that gives me the correct answer. So the amount here is going to be 10. Oh, I didn't think about what the number was. 10,000 something. Let's go back to that. 953.85, right? So again, that 4 has to get rounded up because of that 9. So 953.85. See if I can remember that for 2 seconds. All right, 953.85. I think that was right. You guys can check me on that. Okay. All right, so that'd be the answer for part C. All right, so I'm already over an hour. Let's move on to this next example and get this video over with. So People's Bank offers 5% compounded continuously on CDs. So again, compounded continuously means I got to use this formula here. A equals PE to the RT. What amount invested now would grow to $200,000 in 20 years? So this is flipping the question around. It's not if you invest this much now, how much will you have in 20 years? If you want to have $200,000 as your final amount in 20 years invested at 5%, how much money do you need to invest now? So we're looking for P. What's the current investment need to be, the initial investment, so that it will grow to $200,000 in 20 years? All right, so we'll plug the numbers in. We have 200,000 for A. We don't know P, that's what we're trying to find out. E to the R, that's 0.05 times T, which is 20. So thankfully they gave us an easy time to work with this time. So I need to solve this for P. So now Math Excel may give you a separate formula to memorize here, but I think it's silly to like have a separate formula for this problem than we had for the last problem. It's the same formula. Go ahead and use the same formula, plug the numbers in where they belong, and then solve for the variable that you're looking for. We're looking for P. So to get P by itself, it's being multiplied by this expression. So to get rid of it, we will divide it to the other side. So we're going to divide by E to the 0.05 times 20. I'm sorry, I keep hitting this setup here. I will not wear a hat next time. E to the 0.05 times 20. Divide that to the other side, right? So it cancels it out over here. And again, you might say, well, Mr. Fallon, earlier in the video, you said we couldn't divide to cancel it out. You can't cancel out the base directly by dividing, but if the exponent's exactly the same and the base is the same, and you're canceling out a multiplication, that's the important thing here. This is P times this thing. So to cancel it out, we divide because it's a multiplication. But you have to divide by that whole thing. Otherwise, it doesn't work. So it has to be an exact match for it to cancel out. So this is what I want to type into my calculator, right? So that's going to get P by itself. This is what needs to get typed in. So let me see if this calculator can handle that. So we have 200,000. Let's clear this out. 200,000 divided by, and again, we'll have to be careful with our use of parentheses here. Divided by, which one's division? I feel like I forgot. Okay, divided by, I don't know if I have to, but I'm going to be safe. Parentheses, E to the power of, where's my exponent thing here? To the power of 0.05 times 20. That ends the parentheses. Oh, I forgot the exponent. Oh no. Oh, I got to start over. So I didn't put, I don't know, it won't let me edit either. I forgot to put the print. This will not give me the right answer because what's going to happen is this will give me E just to the power of 0.05. It won't include the 20 in the exponent. And so that will not give me the right answer, unfortunately. So I have to start over. Okay. Oh, at least it leaves that in there. Okay. So parentheses, E. I'm sorry, this video is already going on too long. To the power of parentheses, 0.05 times 20. Close the parentheses on the exponent, and then close the parentheses for the denominator. And this should give me the right answer. And so if we want to have $200,000 in 20 years, we would have to invest $73,575.89 today. And then in 20 years, we'd have $200,000 if we didn't take any money out in the meantime. All right, so help me remember this. 73,575.89. Okay, let's see if I can write that down. 73, I already forgot. 575.89. Okay, I can remember that much. 0.89. All right. And so that would be the amount we want to invest. Okay. So again, I apologize that this video went on a little bit longer than I intended. I will try to do better with section 4.2. So that concludes the lesson on section 4.1. You should go ahead and start on the homework. And if you have any questions, if you're my student, please contact me.